Hi everyone, my name is Bruce and I'm a PhD student working in the Compilers Research Group at the University of Edinburgh. In my talk today, I'm going to talk about how we integrated some solver-aided and symbolic programming techniques into a traditional compiler toolchain that was never really meant to accommodate them. I'll go into some background on solver-aided and symbolic programming, then talk about our representation and how it integrates with the compiler intermediate code. Finally, I'll talk about some interesting ideas we have for exploiting this technique in the future. So what is solver-aided programming? The idea is that we pass some kind of specification to a solver and receive in return a program that is provably correct with respect to that specification. For example, we might specify a program using a logical predicate as well as a potential partial program structure. So here we're asking the solver to find us a program that satisfies for all x, f of x is equal to 3 times x, and is somehow implemented using 2 addition instructions. The solver can then discover a correct program and prove that it satisfies the logical predicate. There are a number of ways that this is used in program synthesis. To give a quick overview, for example, programming by example, where the logical predicate is that the program has to satisfy a number of input-output examples. Or super optimization, where the specification is that the new program behaves equivalently to an existing one, and that it is also shorter or more efficient in some way than the existing one. In this case, a solver is able to identify a 3-instruction program that behaves identically to the 4-instruction program on the left. This talk is going to focus on one particular aspect of solver-aided programming, the idea of symbolic holes within a program. These holes are the interface between the programmer and the solver in solver-aided programming. As part of the specification, the programmer is responsible for providing a partial structure that they think is an approximate solution. Some of the details of this solution aren't yet known, and we write these as question marks. Each question mark is a symbolic hole in the program that represents a value for the solver to identify. In this case, the solver identifies the value x for 3 of the symbolic holes and v0 for a 4th. This produces a program that meets the specification we saw earlier. A great deal of prior work focuses on designing programming languages from the ground up with support for holes or integration with SAT solvers. For example, Hazel is a functional programming language and editing environment that's designed to provide interaction with programs that contain holes and to support user intuition for the semantics of those programs. Another well-known example is Rosette, a language that's designed to provide a toolkit for developing DSLs that can take advantage of synthesis, verification, and SAT solvers. Where there's less prior work and less support is when integrating holes and solver-aided techniques into existing languages. For example, if you have a large application written in C or C++, you have very few options if you want to integrate a hole-driven development methodology or a solver-aided tool into your application. The best option is likely to be transpiling the relevant section of your code into an existing solver-aided language and then transpiling the result back into the host language. This is the problem that I found myself bumping up against during the course of my research last year, and I'll now go into a little bit of detail on the problem I was working on at the time. One of the research projects that I work on aims to rejuvenate legacy scientific software to take advantage of new modern library support and hardware. For example, looking at this code on the left-hand side, we have some legacy application that makes a series of slow library calls to implement some functionality. We'd like for the compiler to be able to automatically transform this code to a new modern implementation that performs the same functionality, for example, with a single call to a modern library. To do this, we use program synthesis to learn the behavior of each individual library function. For example, taking the slow function from the legacy application, we use program synthesis to learn the code implementing that function. This allows us to inline the code back into the legacy application and analyze it using modern compiler techniques and toolchains, even if we didn't know the source of the slow function in the first place. When we perform this synthesis, the language that we target is actually LLVM intermediate representation. This is the language used internally by the LLVM compiler framework to represent programs during compilation. It's a single static assignment representation with a strong type system, and it's not a traditional target for program synthesizers. For our use case, we found that the trade-offs required to implement new synthesis machinery were worth the integrations that using LLVM facilitates. For instance, it allows us to directly inline our synthesized programs into the legacy application without performing another compilation step back to LLVM from a different target code. It also allows us to integrate with several other tools we've developed in our research group for performing code search and description over LLVM IR. However, it does mean that we have to implement some bits of synthesis machinery again on LLVM IR to perform the synthesis. One of these is symbolic holes. The exact details of how we synthesize LLVM IR equivalent to the slow function aren't important for the purposes of this talk, but it's useful to have a rough idea of the first step in the synthesis process to motivate why we end up needing symbolic holes in our IR. The first step of the synthesis process represents programs as a composition of individual fragments. These fragments represent a single program structure or idea. For example, the nested loops in the slow function that we saw previously might be represented at the highest level by a composition of two loop fragments together. Each type of fragment in the synthesizer specifies a recipe for generating LLVM IR. These recipes are independent of possible compositions and can be done in any context. For example, a single loop fragment can generate LLVM IR no matter where else in the program it's instantiated. That LLVM IR looks something like this. It generates a loop header that tests against a condition, and a loop exit block after which the rest of the program can be executed. But it's the loop body that's most interesting to us. Because the loop fragment doesn't know what will be composed inside it, the only way it can express that meaningful computation should occur in the loop body is to leave a symbolic hole. In this case, the loop specifies a single symbolic hole, which says, in the later phases of synthesis, instantiate a single instruction here as loop behavior. Other fragments in the composed program will also create symbolic holes in places where meaningful computation should occur. And it's this set of symbolic holes that forms the second phase of the synthesis process, which we won't cover in this talk. This takes us on to the main topic of the paper, which is how do we represent these symbolic holes within LLVM IR while still taking advantage of the rich set of manipulations, passes, and analyses that LLVM offers us, and without breaking the invariance that LLVM places on its representation. With that in mind, let's take a second to think about the design goals that we'd like to meet with our implementation of symbolic holes for LLVM IR. As well as the basic semantics of being able to substitute values into holes to produce programs, we'd like to have a natural set of LLVM manipulations for programs that contain holes. The ideal is for holes to feel like they are first-class citizens in a program written in LLVM. we'd like to be able to support holes whose type isn't known up front. The use case for this is to implement generic components or fragments. For example, going back to the previous bit of code we saw, the loop fragment shouldn't need to know the type of the data manipulated in the loop body ahead of time. We'd like to preserve as many of LLVM's default compiler analyses as possible. Things like dependency checking, use before definition checking, and other such analyses that allow us to check that programs are well formed are important, and we'd like programs that contain holes to respect these analyses. Finally, we'd like the whole interface to be as general as possible so that a number of different clients could take advantage of it. For example, we'd like to be able to plug in a different solver to our synthesizer, or, for example, to use an interactive programming environment on top of LLVM using the same whole implementation. Let's now look at the concrete encoding of holes in LLVM IR that we use to implement our project, and I'll show how each of these design goals is met by the implementation. The basic element of our representation is to treat holes as function calls. In particular, we represent values associated with a hole as calls to special distinguished hole functions. In the context of the program, these hole functions are uninterpreted. There's no function body or definition available for a hole function, and so the program at large can neither be linked nor executed while holes remain in it. A solver is responsible for examining the value %0 on the slide and deciding on a concrete value to be substituted for the hole. For example, if we thought that the value 5 of type I32 was an appropriate choice, we could substitute for that in the hole to produce a program that could be linked or executed. This encoding works well for holes that have a statically known type when they're constructed. However, our second design goal was that holes shouldn't need to have a statically known type. We want to be able to specify holes whose type is unknown at the time they're constructed. To do this, we'll need to make a small change to this encoding. This change is just to invent a new type that represents an unknown type. The exact details of the LLVM IR on this slide aren't particularly important, but what the idea says is that we're creating a new type that's distinct from every other type in the program that represents holes with unknown type. We call that hole.t in this code example. Then, when we construct a hole whose type is unknown, we simply set the return type to be this unknown type marker. Notice that we have to construct a new uninterpreted function to represent a hole with unknown type compared to the existing one returning I32. By inventing this new type, we're able to encode holes that have a statically known type at construction time, as well as holes that don't have a statically known type. The next question we ask of our representation for holes is how to operate on hole values. For example, if we wanted to add the two SSA values %0 and %1 together to produce a third value, how could we implement that in the presence of unknown types? The LLVM add instruction requires both its operands to be of the same type. There's no way to express the addition of values 0 and 1 together while they have different types. This code is invalid and will be rejected by the LLVM program validator. The solution we propose to this is to use intrinsic functions to mimic the behavior of LLVM instructions. For example, instead of adding an add instruction to the program, here we make a call to the add intrinsic function that produces a value of unknown type, taking as arguments an I32 and a value of unknown type. These intrinsic functions are different to wholes in that their semantics will be later known. Once the type of value %1 has been decided, we'll go into how that happens in the next part of the talk, a concrete implementation for the add function can be generated for the particular types. For example, if it's assigned type I32, then the instruction selected will be an add instruction. If the integer size selected is different, then we might end up needing a truncation or sign extension to implement the addition. We mimic these intrinsic functions for each of the LLVM instructions we might operate over. For instance, arithmetic, bit shifting operations are all implemented using these intrinsics. The final piece of our implementation is how we manipulate LLVM IR programs that contain whole values. To describe how we do this, we'll first have a little look at how LLVM implements similar transformations on programs where all the types are statically known. Looking at this example code, we have a whole value with known type of I32. LLVM provides a primitive transformation called replace all uses with, or RAUW. The semantics of RAUW are simple. It replaces every instance of a particular SSA value in the program with another value. For example, looking at the code at the top of the slide, if we want to replace all uses of the value %0 with the integer literal 5, we get the resulting program at the bottom. Crucially, the original value %0 is now never used anywhere else in the program and can be removed as dead code. We need a version of RAUW that can work with values of different types, that can choose a value for a whole type whose type is unknown ahead of time. Let's now look at the behavior we expect from a replacement for RAUW that allows us to change or assign a type to a whole that doesn't already have one assigned. The code here at the top of the slide is similar to the previous example, except instead of an I32 typed whole, we have one with an unknown type. The add call in the second line is the same behavior as we saw before, except using an intrinsic function because we can't use an add instruction. The implementation we demonstrate that replaces RAUW is called RAUW NT, short for new type. It mirrors the behavior of RAUW, except that the type of the replacement value is specified along with the value. At a high level, the semantics we expect to see after an RAUWNT call are something like this. As before, the replaced value, %0, is dead. The value 5 has been substituted into all the places where 0 was used previously. Additionally, the type of the second expression has changed to I32 because the type of both of its operands are now known. The add intrinsic function has also been resolved into an add instruction. There are a number of subtleties and difficulties to implementing this inside LLVM without breaking the program invariants. Implementing this transformation on a program using LLVM's existing machinery requires us to perform a fair bit of trickery. The exact details of how we do this are beyond the scope of this talk, but if you're interested in what we do internally, I'd encourage you to post a question in the chat or come and find me afterwards. A high-level overview of how we do this is essentially deleting and reconstructing values in the program to give the appearance of assigning them a new type. The whole of unknown type in the previous example is actually deleted from the program and replaced with a value with a similar name with type I32. This can end up propagating changes of type through the program at some distance. For example, intrinsic functions, like add, as we saw there, end up receiving a type when one of their operands receives a type. This can have a knock-on effect, changing code at a distance in the program. This doesn't typically happen using LLVM's default RAUW. Implementing this deleting and reconstructing is unsafe in general. It changes the structure of the program in a more fundamental way than RAUW will ever allow you to do by default. Our implementation takes this unsafe core operation and wraps it in a safe interface that provides the programmer with a record of what was transformed within the program and makes guarantees on the safety of the transformation. To quickly summarize what I've talked about today, I've given some motivating applications for programming using symbolic holes, such as interactive programming and solver-aided programming. I've shown an encoding of symbolic holes in LLVM IR, which is a language that was never intended to support holes originally. Finally, I've shown the program manipulation primitive that allows us to effectively change and transform these programs in the presence of holes with unknown type. We've got several ideas for interesting future work using the tools we've developed. We'd like to develop embeddings into source languages that target LLVM. For example, developing a DSL within C or C++ that allows for programs with holes to be written in those languages. They could then be compiled down onto our language LLVM with holes. We could look at re-implementing some existing programming with holes applications using LLVM with holes. Finally, it would be interesting to examine the semantics of the resulting language. There are several existing attempts to formalize the semantics of LLVM IR, and it would be an interesting future task to add in support for holes to these semantics. Thanks for listening to my talk, and I look forward to answering any questions you might have.